Difference quotient, huh? Do you remember that? Does it ring a bell? Is it somewhere in the recesses of your mind? I know as a student, I did not. I must have missed that day. I must have been sick because I didn't know what the difference quotient was. And it's kind of notationally dense. So we're going to take our old slope of the tangent line formula. I told you we're going to change it. We're going to switch it up now. You can still use it. It has a value. And I'm just going to show it a little bit different from here on out. And I'll tie it back in at the end. Here's the slope of the tangent line. The slope of the tangent line formula. Where when those x values get closer and closer to the a value, the functions get closer together. And then we end up with that thing where it's like, hey, as they get closer together, you get that 0. And then you get 0 up top. And then we pretty much learn that 0 over 0 can pretty much equal anything. Yeah, that's kind of the game. Hopefully you've caught that by now, that 0 over 0 turns into all kinds of crazy shit. But what's dope is it's not just anything. In this case, it's actually going to be the slope of that little, like, you got a point here. It's the slope of that thing. That's pretty dope. This thing is going to, like, the power of this, I'm not sure if you catch, like, do you know that everything changes? And being able to capture the change in that one instant? Powerful. I don't care whether you're talking about biology and how cells are actually, I shouldn't even start talking about anything that's to do with science because I'm talking out my ass. But your field, think about how something might be changing. That's what calculus is talking about. How we're going to be able to look at it, even when shit's weird, like a 0 over 0. We're gonna pop it out because of badasses like Newton and Leibniz coming up with this shit for us. Because me, I'm just parroting this stuff, acting like I understand it. I'm a parrot. I barely understand. The badasses were the Newtons, the ones that truly understood this. And now anybody can come and understand it. Because if I can understand this shit, trust me, you can understand this. Just a matter of time. All right, I'll shut up off the damn soapbox. Let's go. Here's our new formula down here. This is the difference quotient. Right in here. This is actually the difference quotient. Hopefully your teacher in an algebra class has shown you this before. It kind of takes a little of the sting away because this is our new process for a little while. I'm going to force, this is going to be one of the written components on your first test. It's going to be a delta epsilon, and then you're going to have to show me this by hand. It's just algebra. It's a big algebraic mess, but for now, we're going to manipulate the equation that's up top, this one here, and we're going to turn it in, we're going to and pop it right into this and show it's the same thing, just written a different way. It's just, I prefer to use the one down below, and it kind of has a little, it's just used more. I don't know. They're both valid. Whatever you prefer, and I'll tie this one up top into the derivative formula as well. Oops, I think I said something wrong. So these are equivalent. They're the same thing, but let's go for a little ride. Let's say x is equal to a plus h, right? Because I'm just looking here and going, like, can we just change that? I mean, that has to be the case. Like, this is x and that's a plus h, so that looks like a good starting point. I'm kind of begging the question here since I'm showing you where we're supposed to get, but maybe it helps to understand. Oh, let's manipulate this and let's write the limit. And I'm not going to write anything in the bottom for now because I'm going to change something. Just a second. I'm going to leave the f of a alone. I'm going to leave the minus a alone. The only thing we're changing right now is the x. And since the x is written in here, that's why I'm leaving it alone for right now. There's going to be a big old, hey, did you see this? And if you catch it or not, who cares? All right, so instead of writing this x value in, x and x, we're going to say a plus h, right? Because that's what our x is. Okay. A plus h. A plus h. We should put a parenthesis typically, but since there's no plus, but just be careful with that shit. When it's behind something, careful with like those minus signs. We tend to make those mistakes. I know I do. So I look at this and I look at the denominator. Notice how those a's are just gonna go away, and that's gonna match the bottom. Now here's the weird. Since we have the limit of x tending towards a here, let me manipulate this because I want to make it the limit as h is going somewhere. So let's see if we can't see something. And let's just, I'm just going to subtract the a over and just look at what's, and claim that x minus a, that's equal to h. Well, wait a second. Aren't our x's going towards our a? So where's our a? What would be the distance between something that is going right next to each other or going towards each other? When something collides, how far away is it? 0. So what we're actually going to say is it's the limit, oops, shit, I already wrote that, as h goes to 0. It's the same thing as that x getting closer to that a value, right? The difference between x and a is going towards 0 as they get closer and closer together. Yeah, they're going towards being the same thing. If x minus a was going to be 0 before, in the denominator, remember this? 0 over 0. Yeah, that's why that h is going to 0. So this is the same equation, just played around with. So this is our new one. This is what we're going to mess with. It's the same formula, just manipulated. Now let me show you some other things that go along with this, the slope of the tangent line. Hey, this is the velocity formula at some point A. This is the wait a second. These two look kind of similar. Kind of look similar. Because they're the same frickin' thing. They're the same thing. You can actually model velocity, and we're going to do a whole video just on that. You can model velocity on the change in your distance. Think about sitting in a car. Huh? The change in your distance. The instantaneous rate of change of your distance with respect to time. Look, change in distance. Like miles maybe per a time, like maybe hours. It's your speed. Well, velocities, but we'll talk more about that later as well. So this models this. The change in your distance, or your position, the change in your position with respect to time is your velocity. And we can model it with derivatives. And then we have this new thing, and I just said, oh my gosh, did I say derivatives? Oh, the point of calculus. This is the shit we talk about the whole time. Calc 1 is the derivative class. We're finally here. Here's the frickin' derivative. The derivative of the function at some number a is this same frickin' formula. It's the same damn thing. So this is what we're going to be calling, when we say the slope of the tangent line, that's the derivative at some point a. We're saying the same thing at some number a. X equals a, and we have this new notation. This is it. This is the big thing. F prime of a. We're going to be reading that again. That's F prime of a. So this little apostrophe up here, this is huge. This is it now. We're going to start writing like this, and there's a couple different notations for it. We're going to start off, and I'm just going to write it like this for a bit. And a little ways down the road, I'll start showing you the different notations. Trust me, this is plenty of actually, I probably don't need to tell you this is plenty of notation already. But what we're saying is the instantaneous velocity at a point, at some point in time, is the same thing as the slope of the tangent line, which is also the same thing as what we call the derivative of a function at a number a. So 2.7 is all about finding it at just a point, this derivative. 2.7 is just about finding the derivative at a point. 2.8 will find the derivative as a function. Not at a point, but for any point in its domain. That'll be the difference. 2.7 and 2.8 are very similar. It's almost the same thing. It's just in 2.7, we're just talking about an instantaneous points, just finding the slope. In 2.8, we're going to start creating whole new functions that can model other functions and how they change. This shit gets dope. It gets fun. If you jump into it and you try and do your best through it, you can kind of you'll start to see the world a little bit differently. I promise you. Because we can tie in this little math, and you can see the math in nature and shit. So, I don't know, I'm a nerd. Maybe it's all stupid. Whatever. But Yeah, we'll come back and I'll show you the more of the how, and we'll do some velocity a little bit later.